can confirm that they can see the screen. I have not shared. What? I have shared. Okay, I'll try to share it. Yes. Okay.
Yeah, we see it, I think.
Perfect. And you can hear me also.
Yes, clearly.
Great. Thanks. Switch off. That side small window. Now this is fine. Right. Okay. Perfect. Okay, so we are going to study stars. Okay. Want to learn something about stars? Good. Very good. Okay, so there are three lectures on stellar structure and distribution. This means we are talking about general stars. Okay, who will tell me? Like this is like a buzzer question. First answer. The name of the star nearest to Earth. Okay, good question. People usually answer Proxima Centauri. We don't even bother that the sun is a star. Sun is our only daytime star. That's all the stars come in the night. Okay, so this is a full flash, it's like full flash semester course on stellar structure and evolution. You have to finish in three lectures. All right, so we will be very brief. I won't go in much details of like mathematical details and all, but I will try to give an overall feeling of the topic. So, what is a star? A star is something which is held together by gravity. Okay, but if gravity is holding something, so you need something to hold the gravity also. Then only the equilibrium will be maintained. Okay? All right. Now we know that stars usually radiate all the time. So this means there will be some energy source in the central region of the star. That's why the energy keeps coming out. And probably that energy source is responsible for holding the star collapsing against its own gravity. Okay. Now, when we study stars, so we usually make some assumptions. Okay. What assumptions? First, we assume that stars are spherical. Okay. And they are symmetrical. Of course, they will be spherical, they will be symmetrical. Second, we ignore rotation. So we are just assuming star like a ball, which is not. Because if you consider rotation, then there are many more things come into the picture, and with that way your calculation becomes extremely complex. Third, outside gravitational influences are ignored. This means we assume the star to be an isolated body. We are not bothered about something which is like, suppose there is a binary system, there is another star nearby which can affect the motion and the dynamics of that star. So that also we are not assuming at the moment. Fine, very small things. We assume uniform initial composition. This means we assume the entire star to be chemically homogeneous. This is also an assumption. Initially, we assume Newtonian gravity. This means we can apply Newtonian law, Newton's laws, planetary Kepler's law, and all. Okay, we are not considering general relativistic effects. Fine. And then one thing we also assume that stars change slowly with time. Yes. Okay. So what is the meaning is that the time period when we are concerned that we are not like bothering about whether the star's chemical composition will change or its mass will change or luminosity will change over a short period of time. Okay? Right? And then the most important of all, that stars can be considered black bodies. Everyone knows what a black body is. What is a black body? That absorbs all the electromagnetic radiation, whether it emits? No. Yes. Possibly. Emits as well as absorbs. A body which is black is a black body. Fine? Okay. These are the questions we ask in our PhD entrance exams. Interview. I will tell you some, if you want to know more about it, I will maybe ask you. I will tell you. Alright. Now, if you want to study the evolution of the star, means okay, how it started its own life journey and how it will evolve in future. This requires the knowledge of three main parameters, which are mass of the star, radius of the star, and its luminosity. The luminosity is some sort of, you can imagine slightly it is related to temperature of the star also. Okay, but you can see these three quantities. Along with these, okay. So one thing I want to tell you also that in astrophysics we usually express mass, radius, and luminosity of anything. Usually in stellar physics, in terms of solar units. So suppose there is some star, say Betelgeuse. Everyone has heard about Betelgeuse. Okay, you are going to see also in a couple of days, next week. Okay, so we can say the Betelgeuse mass is how much? So you won't say that this is like some 5 into 8 into 10 to the power 55 grand. No, 2 solar mass, 3 solar mass. This is a convenience. Okay. Similarly, we say it's like the star is like its radius is like 2 times solar radius. Even when we talk about the supermassive black hole, which are residing at the center of galaxies, there also we talk their mass in terms of solar. Just a convention. And I don't know that I think someone might have told you that in astrophysics we stick to CGS system. We don't use NKS system. You know NKS system? Meter, kilogram, whatever. Okay? We stick to CGS. That's why you will hear a lot about like say Earths per second when I talk about. I will not talk about watt or joules. Earths per second. Okay. This is just a convention. Just a convention. Fine. So along with these three quantities, we also need relative abundances of all chemical elements. Why? Because you know that I'm sure you are familiar with the nuclear fusion and all. So you know that the nuclear fusion happens in the central region of star. So the hydrogen will fuse to helium, helium will fuse to something. So you know that you need to know that at a particular time, what is the chemical composition of that star? How much fraction of the total mass is helium? How much total fraction is carbon, silicon, etc. So this information is also needed. Got it? Fine. Everything's fine? Good. Okay, let me talk about something about stellar spectrum. You are studying photometry and spectroscopy for the last 2 days, so you are expert. So I don't have to go in that detail. So I will tell you the spectrum of the star consists of a black body radiation coming from the inner region of the star. It's like a continuous radiation. Who are you?
Sir, I'm a JRF.
You are a JRF. You have joined recently?
Yes.
Okay, so black body continuum radiation means like suppose you have some iron rod and you just increase its temperature. What will happen? Slowly, first it will be slightly bit warm, then it will be a bit more hotter. You cannot hold it on your hand. Okay, then slowly it will start emitting radiation. Okay, even if you can wear IR goggles, you can see the radiation window. But from your own naked eye also you can see slowly it will become red, then whitish color, then bluish, and then you will not see anything after that. Because when we are looking at UV region, if you can keep increasing the temperature, the rod will start emitting X-rays, and then gamma rays also. Who knows? No, but by the time the temperature needed to reach that level of radiation, it's not feasible, you can say. Okay? So typically, to emit X-rays of say 1 kiloelectron volt, we need a temperature typically of the order of 1 million degree Kelvin. So 1 gamma ray photon we need 1 billion degree Kelvin. How will we like produce 1 billion degree Kelvin temperature? Alright, but in the star's interior regions of the star, the temperature of the order of million degree Kelvin. So they emit like a perfect black body, and you understand this will be a continuous radiation. Like the black body spectrum you have seen. Well, let me draw it. You must have seen, like if you have on the y-axis you have f nu, on x-axis you have nu. You must have seen this is like a black body spectrum. Planck's law. Everybody has heard about. Fine. Okay. So you know that this is a continuous radiation. There is no emission or absorption features. There is a continuous radiation. Continuous spectrum, absorption spectrum, emission. You have studied everything. I'm going to teach you. Alright. So this means this continuous radiation is coming from the inner regions of the star, but the outer regions of the star is relatively cooler. Outer layer, which is called photosphere and all. So what will happen? And this outer layer will have some chemical elements, magnesium, silicon, hydrogen, carbon, helium, carbon, whatever, anything. So these cooler layers, they will absorb some radiation. So what you will be getting, you understand, you will be getting some continuous radiation, and on top of that there will be some absorption. That's how absorption spectrum is formed. Understood? Okay, let me show you a photo. So you see, this is a typical spectrum of a star. So you can see here that you can understand this is the continuum, black body continuum. Okay, and on top of that we have these absorption features. Fine. And you understand these absorption features tells us about the chemical composition of that environment. Okay, that's why spectroscopy is a very important field in optical astronomy. It tells us about the very inner things, what is happening there, chemistry. Clear? Okay. Because I'm going to use this when I will teach you EGM. Okay. Now you know that there are so many types of stars. Stars are classified using different classification schemes, but one which is most common is something called based on the relative strength of their absorption lines. So in some sources, say for example this line, which is the H beta line at 486 nanometer, will have this strength. In some other star, if you take the spectrum, this line will be much deeper, much stronger, and this will tell us something else about that star. So this means all stars will not have exactly same type of optical spectrum. Okay, it varies as the property of the stars. Okay, so stars are classified based on the relative strength of the absorption. Clear? So people have defined earlier that we can classify stars by giving this sequence OBA FGKM. Well, it doesn't look like any sequence, but I don't know. It's like a historical people have defined. And later people also use LD. So the one way of remembering this, that's what I read in books. You can remember like, oh, beautiful and funny guy or girls kiss me. That's how people have told it. That's how you can remember it. OBA FGKM. So what happens here? O-type stars, I will show you. O-type stars are the hottest stars. They are the biggest stars, bluish stars. And if you go as towards this side, the star's temperature decreases. Okay, so you understand that the star's temperature decreasing, this means its black body spectrum, which is peaking at certain wavelength, will go toward longer wavelength, means shorter frequency. Clear? Alright. Now, for example, if you talk about type A star have the strongest hydrogen absorption lines. Okay? This is the shape. Nominally. Don't worry. Okay? And these spectral types, they are further divided into 10 subclasses, say A0, A1 to A9. With a higher number assigned to other stars. So if I tell you A0 and A9, which star is hotter? A0. Okay? So if you are observing two stars, say A0 and A9 star in blue filter, which star will appear brighter? Clear? Okay? Alright. Now, people have also done some more subdivisions based on the Roman numerals, say 1 to 7. So you can have A01, that Roman one. Okay? And this one corresponds to this is for the signs. One corresponds to supergiants. Stars. If you go to YouTube, okay, and you simply search in YouTube, scale sizes in YouTube or something like that, you will be very big videos. And then you will realize how tiny we are. Insignificant. Okay? And then I will keep realizing you these things over and over when I will teach you many more things. Alright. So here is the table. You can get some idea here. We have different types of stars, OBA and TKM. Then you can see color. Blue, white, creamy, yellow. You see how this color corresponds to the wavelength where black body spectrum is peaking. Clear? So as the temperature is decreasing, you can see the temperature 35,000 Kelvin, and it is coming around 3,000 Kelvin. So that's how corresponding your black body spectrum will shift toward the longer wavelengths. So corresponding the primary color that you will see will also shift toward the redder side. So redder means lower energy, bluer means higher energy. Fine? And you can see some photo here. Okay? Our sun is, I think, what type of star it is? What? Anybody taught you? You know it, or like somebody has covered this? Or you know it? Good. So our sun is a G type star. G type star, I don't know. This is the, we can see this is a typical optical spectrum of different types of stars. So really they are dominated by, and in fact you can see on the x-axis we have wavelength. You see as the temperature is increasing, this peak is shifting toward the left hand side. It's not very clear, but you can guess. But this is that's what this is a black body. On top of that, we have absorption lines. But the continuum is a black body. Clear? Okay.
What is the normalized flux on the wire?
Normalized flux. So you see some star will be bright, some star will be faint. So if you want to plot two stars which are having very huge difference in the flux values, okay, so we have to do some sort of normalization. How we can normalize? Say for example, you take the spectrum of a star. The spectrum is what? Wavelength as a flux as a function of wavelength. Okay, you will get some flux values as you can see in this figure. Yes, like this. So you pick any say at 500 nanometer, what is the flux? Some flux, you divide the entire flux value with this number. Okay, and you do this the same for all spectra. So this is some sort of normalization, like something like bringing everything to a common platform. Got it? Practical example also you can.
Is energy source here the element which is causing the absorption?
Yes.
Why is it energy source?
Energy source? What energy?
Why is it called energy source?
Energy source here, no. Here the meaning of energy source is that what is the primary mode of nuclear fusion? Nuclear fusion can happen hydrogen to helium, but helium to carbon also.
But why? Energy source for all of them would be mostly hydrogen. Why is it hydrogen?
No. So you see here, I think this has more to see that because you have 3000 Kelvin temperature. Okay. So do you know that at 3000 Kelvin temperature whether the nuclear fusion of hydrogen atom will happen? Probably not. So hydrogen burning may not be the primary energy source here. Okay. I will remove some slides in between. Okay. Because I could explain that why you see these, you can see here some like emission features. These are emission features coming from the metal. So these stars have metal in their environment. Okay. So how they are produced and all that might be slightly deeper. We can talk later also.
Sir, what about the slope in that shorter wavelength?
What?
The slope.
Slope. So you see, I told you, you have normalized. But one is here, slope tells you, that's why I was telling you that as you going towards from say M towards O, your black body peak is shifting towards the lower wavelength. The peak is going other way. Fine. Here you can see it is peaking somewhere here, then here, then here, then
slope
here.
is higher as well.
Yeah, it becomes more prominent. Okay. Fine. There's something called color index. You have studied this?
Sir, how will the spectrum shift if there was a flare?
Sorry?
How will the spectrum shift if there was a flare?
Like flare in which band you are talking? Of course, see, if you are observing a star, you are observing the star in say optical, infrared, UV, X-ray. When you are talking about a flare, so flare must be happening in some particular filter. Depends. Okay, so the answer to your question depends like in which band the source has started showing flare. Got it? So usually, see, one type of flare is that your only flux level has increased. The source suddenly became bright. Okay. The another type of flare is that not only flux has increased, but the energy of the photons have also increased. Okay. This means earlier the star is emitting some number of photons. Now it has started emitting more photons, but of same energy. So your spectrum shape will not change. Only it will go up or come down. But if the star has started emitting radiation more with higher energetic photons, so the spectrum will shift towards the lower range. Okay? Got it? Color index. Somebody has covered? No, nobody has covered it. Okay, I will teach, no problem. You know that, apparent magnitudes. Apparent magnitude everybody knows. That I am confident. Okay? Okay. So these apparent magnitudes can be considered as a proxy for the source brightness. So we all know that smaller the magnitude, brighter the source. This is also very clear. Okay. Now apparent magnitudes are measured in particular filter. So we cannot just say that a star has a magnitude, high magnitude. As I ask this question immediately. What band you are talking about? Which filter? You have to be specific. So, for example, when we say in V band, the apparent magnitude of a galaxy is 15 band. So you have to define a band. Band means a range, wavelength range. Okay, you have a telescope. So the CCD of that telescope has a range. It won't observe photon of single wavelength. Okay, it will observe over a range. That's why it's called band. Okay. Now, the use of filters to measure apparent magnitude of stars in U band. U band, I'm mentioning only one wavelength, which corresponds to the wavelength at which its filter response is peaking. It does not mean U band meaning only 3640 stars. It may be say from 3500 up to 380 with a peak coming around 250. Okay, B band and V band. So when we study stars in these three filters, U, V, and V, so this is usually we call UVV photometry. You can understand that U color corresponds to more higher temperature, more energetic. Okay, higher temperature. Understood? Yes. Head nodding is very important. So that I should be convinced now that you are understanding what I'm saying. Okay. Now let us consider a situation where the star has a magnitude MB and MV in two filters B and V. Okay. Now, if we take the difference of these two values, MB minus MV, we are just writing as a B minus, just nomenclature. So this MB minus MV measures the relative flux in the B and V bands. Okay. In other words, this B minus V, or say this difference, can be considered as a proxy for the temperature following the Wien's law. How? Suppose if the star is hotter, what will happen? MB will be larger or MV will be larger? V will be larger. Because larger means less bright. Okay? So if this is the case, this means if this difference is positive, this corresponds to cool stars. Because then this means your B is larger compared to V. Larger means enter. Okay? And if it is less than hot stars. You understand? You do not need any distance measurement to calculate the luminosity, etc. Just by measuring the source apparent magnitude in two different filters, and taking the difference will tell you the approximate idea about the temperature of the star, whether it's a hot star or a cool star. Okay, fine. See, B minus V is just an example. You can take any two colors. V minus R minus I, U minus me, U minus R. Let's say depends depending on the what kind of instrument you have, what kind of telescope you have. Okay, you can define any two. So this means this magnitude difference. This is what I did not mention. Basically, this difference is called color of the star. So negative means color is bluer. Negative color means bluer star, isn't it? Good. Okay. Now, using these trivial concepts, in 1912 there are two scientists came up, and they proposed one, we can say, it's a revolutionary idea called HR diagram. Okay. So not 1912, 1911. They plotted the luminosities, or say brightness of the stars, versus their color index. So color index you understand is B minus V. Right? So you can put B minus V color index on x-axis, and on y-axis you have luminosity or brightness. Fine. And on this diagram, then you plot not only one star, you plot a bunch of stars. Okay, why we plot bunch of stars? Why not only one? Because we want to understand the overall population. Say for example, if I give you one very simple example. Suppose if a mosquito wants to study the life of a human, how a mosquito will study the life of a human? Its own life is. Okay, so in its entire lifetime, mosquito cannot even study even minute change in the life of human, isn't it? We are just like that in cosmological context. The sun's state is not changing life of human, then what the mosquito has to? Mosquito has to come to us. And it has to just roam around and see different types of people. Some will be young, some will be old, some will be on the verge of getting old, some with hair, some with no hairs. Okay, so this means you need to see a population, and then try to study the overall population, and then try to make some sense. Whether are you seeing any pattern? Okay, so you understand in astronomy, this means we do two types of study. I am talking about the observational astronomy. One, you do source specific study. You are studying only one type of object. Or second thing is called population study, where you take a sample of sources and you see how overall populations they have. Got it? So basically what they are doing here, they are doing the population study. And I will show you the picture, and then the meaning becomes immediately clear. This is a Hertzsprung-Russell diagram, and this shows the relationship between the stellar brightness and temperature. So you will see, I will tell you, one star will not move everywhere in this HR diagram. You have a bunch of stars. Some stars are lying here, some stars are lying here, some stars are lying there, some are here, some are here, some are here. Meter please. Microwave. Okay? You got it? Now we are going to study this in much very detail. Next two lectures will be only on this evolution. Then you realize the power of this diagram. This is very important. It means there is a science behind each and every slight change in the curve, or say tilting, or whatever you are seeing. Everything has a physics behind it. Why there is one branch here, and then what are these objects? We'll see. Okay. Theoretical HR diagram. You see, this is observation. Means you observe a bunch of stars, you measure their luminosity, you measure their color, and then you plot. Fine. People can do the same thing from theoretical perspective. So from a theory, what they plot luminosity versus spectral type. Spectral type means OBA and GKA. Okay. Observation people plot color indices. Because that's what we observe. Okay. Fine. One thing we are noticing, you can see this. Yes. You see, this is the hottest stars. The temperature is highest here. These are the hottest stars. That's why they have color violet. Okay, these are the hottest stars. They are up left. Cool, dim stars, because you see they are the brightest as well as hottest. Cool, dim stars, low right. Okay. Then we have a dim but hot stars. Dim means they are very end, but their temperature is very different. I can give you 10 examples of daily life just on this diagram. You can think of it. Okay. And we have a bright but cool stars. Upright. Okay. And one thing one can immediately understand here that this entire diagram doesn't look like a randomly plotted point. There is a pattern. Okay, that tells us about the evolution of a star that we will study tomorrow. And in this diagram, this middle region, this is called the main sequence. Okay. So usually stars they spend around 80 to 90% of their lifetime in main sequence. You can see so you can get an idea here that because this is a childhood days, there's a adult days, and then you are growing old. And that's what happened. That's true. And ultimately you die. That's what. Okay. So in main sequence, stars fuse hydrogen to helium. This is a nuclear feature. Clear? Now, position on the main sequence depends on mass. Do you understand? This one star is here, like the sun. It has some mass. This is also main sequence, and this is also main sequence. Okay. So why our sun is here but not here? Because of the mass. That's what this sentence says. Low mass in lower right, massive stars up left. So this means, in other words, you can understand as the star moves, its mass increases. How? We will study. We will study later. We will study. Okay. This I already told you. Now you know this is the branch called giants. Horizontal branch. Giants means the stars are big. That's all. Okay. Just imagine this is suppose this is the sun. Then these are the giants. And these are the names of some stars. You can see this Spica, LD, whatever. And then Antares, then Betelgeuse. These are the names of different types of stars. You can search in Google later. What are these? You will find very interesting things. Okay? What are the giant stars? They are evolved stars. And I told you they have already passed most of their lifetime, they are already evolved. Okay? They fuse helium to carbon or oxygen. And you can see this main sequence and this horizontal branch. This is very clearly separated. Okay? We will study all these things in detail. Why? So you see these stars have temperature, but they are luminous. So this means that you understand. Suppose there are two stars of same luminosity. One is smaller, one is bigger. So which star will have lower temperature? The bigger one. Because surface area is large, isn't it? Yeah. Good. Supergiants. These are the most massive stars. Like when I say most massive, I do not mean like it's like 1 million solar mass or something like that. It's like 10 solar mass, 20 solar mass. Means a star as massive as like 20 suns. You put 20 suns inside that star. That is. But still it's too much. Okay, then we have on the bottom left, we have white dwarfs. As the name suggests, dwarfs. They are tiny. And these are called, this region is called stellar graveyard. As I told you that the star, we will study this in detail, but I will tell you that ultimately most of the stars end up being. Not all stars undergo supernova. Okay? Only some stars undergo. Some cricketers they retire first, then nobody knows even this guy will retire. And when Sachin Tendulkar gets retired, then the whole world is watching. Okay? So now these are small white dwarfs. They are very dim, but they are very hot. Okay? Fine. So HR diagram, you got some approximate idea. Okay? More details we'll study from tomorrow onwards. I want to spend rest of the day half an hour on time on stellar structure. So suppose if you want to study a star, okay. So how we study? When I say study a star, what do I mean by studying a star? Means I want to understand its physical properties, whether how it's like what is its mass, what is its radius, what is temperature, how mass changes as a function of radius or as a function of temperature. Okay, these are the things. Do you understand? This means we are going to deal with physical equations governing the property of the star. Say for example, you have a black body. So for the black body radiation, the governing equation is Planck law. Okay, simple. So it's an equation. Similarly, for the star is a set of equations. So there are set of equations to understand the structure of a star. A stellar structure means structure of a star. A stellar does not mean anything fancy. It's like a structure of a star. Okay, so let us consider an isolated, static, and spherically symmetric star. Isolated means we are ignoring the gravitational effects of any nearby or any other astrophysical object. Static means we are not considering rotation. And spherically symmetric means we are assuming it's a perfect sphere. Okay? Alright. So there are 4 equations to describe the structure of a star. First equation is called conservation of mass. We will study. Second equation is called equation of hydrostatic equilibrium. This means at each radius, forces due to pressure difference balance gravity. So you imagine one star, you consider a layer in that star. You understand there is a gas below that layer which will try to push this layer up. This is a gas pressure. Okay? Then there is a mass on top of that layer which will try to push it down. So as long as there is a balance between this pressure difference and the gravity, the system is stable. Understood? So you understand why we need equation of hydrostatic equilibrium? So this is going to tell us about structure of that star, whether the star is in equilibrium or not. Third thing is called conservation of energy. So this tells us at each radius, the change in the energy flux is the local rate of energy release. What is the meaning of this? Suppose again you consider a layer. Okay. Suppose below this layer, some radiation is flowing out. So suppose some energy flow rate is say E1 below this layer, and then you measure it again on top of that layer, it becomes E2. So this means the difference is E2 minus E1 or E1 minus E2, whatever it could be, is due to the energy being generated or absorbed in that layer. So that is the meaning of this. The change in the energy flux is the local rate of energy release. Clear? And the fourth one is called equation of energy transport. So this tells us the relation between the energy flux and the local temperature gradient. How temperature is changing as a function of radius, and then how it affects the flow of energy flux. Got it? Only 4 equations. Entire stellar physics is based only on these 4 equations. I haven't shown you equations, I have shown you the description of them. Okay? So let us derive some of the equations. Okay? Actually, all these things I have taught in our MSc in astronomy course. We have MSc in astrophysics, 2-year course. First year you will study Pune University, second year you will study in IUCAA. So people who are doing BSc, you are in BSc final year, can think of applying for this MSc in astrophysics course. I will discuss these things later. I will teach you gamma rationale. Okay, let us come back to conservation of mass. So consider a thin shell inside a star having radius r and thickness dr. So at the radius of r, we have a shell of thickness dr. Okay. So what will be the volume of this shell? You understand? It will be 4 pi r square dr. Clear? And what will the mass of this shell? Dm. Because it's a small shell, it's a infinitesimally thick shell. So we can say its mass is dm, which will be the volume multiplied by density. And since we are at a particular radius r, so we have a density at that radius. This means density could be radius dependent. Okay, and in fact density will be radius dependent. In ideal situation, we can assume homogeneous medium and all, but in reality, so this is the mass of the shell. Now you have learned convention of mass. So then what you do? You can do dm by dr equal to 4 pi r square rho r. So what this tells us? This tells us how mass is changing as a function of radius and how it depends on the density of the material. Okay, this equation is called mass conservation or continuity. Fine. Okay, who is sleeping? Nobody is sleeping. All right. Second, hydrostatic Paliya. Consider again, you consider a small shell, and rather than assuming the whole cell, I am considering only a small element. Okay, you imagine that this is a star, and you consider a small element in that star. Okay, at a distance r from the center, thickness dr, and at that position, assume the density rho r, and assume this surface area of this element is a, and thickness dr I told. Okay. Now, the outward force will be pressure on the bottom face, PR. So the force outward will be PR into A. Let me see who is sleeping. Yes, you. Yes. How force becomes PR into A? No, behind you. Yes.
Pressure, but force is pressure into it.
Force is pressure into area. Okay. Good. What is your good name? Okay. Fine. Got it? And what will be the inward pressure on top of the surface? Let us not worry about gravity at the moment. Let us worry only about the gas pressure. So at R plus dr, the force will be PR plus dr into A, which will be inwards, because gas is putting the pressure in all the directions. Okay, so the gas which is on top of this will try to push it. Okay, and what is the pressure? Pressure will be PR plus dr. It could be greater than PR, it could be less than PR. We do not know it, but whatever it is. And then along with this, you have a mass of this element, gravitational force. Okay, and that gravitational force will be G mr dm upon r square. How this comes? Mr is the mass below this layer. You know formula G m1 m2 upon r square. M1 is my mass of the rest of the mass which is inside this layer, and dm is the mass of that element. Got it? So if the system is in equilibrium, you understand these forces they should be equal. Okay, and you can write dm as rho into A into dr. अरे वो 4 pi r square dr में 4 pi r square A होंगी ना, ठीक है? Who didn't understand this? Please do not think. I am like talking to you like very informal way, because so that you shouldn't be scared of asking questions. Feel free to ask anything. This is your first introduction to astronomy. First time you are seeing what you do in astrophysics. This is the time to ask questions, to learn it. Okay? Don't hesitate. Just ask. Whatever non question you have. No worries. Okay. So in equilibrium, we have PR into A will be equal to PR plus R into A plus this form. You can do rearrangement and then you will arrive at this equation. This is homework for you. That how will you reach here from here? It looks trivial, but do it. That will give you the feeling about you. Okay? See, I will tell you one thing I learned when I was like of your age, when I was doing my MSc in IIE. So one teacher, he taught me several courses, but in one of the courses, she told me one thing that Vaidehi, it is very important to keep a habit of writing. Because I will give you these slides and then you will have all the material, you may not have to write anything. But it is very important to make a habit of keep writing things. That helps in like clearing your concept. And second, I'm sure you all have. You should also have a develop of drinking water regularly. You sleep will not. Okay. Now, in the limit as dr tends to 0, this week I can write as dp upon dr. This is universal mathematics now. Differential mathematics. No? Okay. And then you have ADR got cancelled out, and we have dp upon dr equal to minus gm by r square times rho. This is the equation of hydrostatic equilibrium. Again, you understand this tells us how pressure is changing as a function of radius and how it is connected with the mass of the element, means gravity. Okay. So second equation also everybody understood? Okay, let's go to third. But before going third, let us do one more. See, using this equation, hydrostatic equilibrium, this tells us about the how pressure changes as a function of radius. So this means using this equation, we should be able to calculate the pressure at the center. Why not? Okay, let us do that. So we can estimate the central pressure. You see, this is what steel structure is. You are studying the structure of a star. What is the pressure at the center? What is the pressure at certain radius and all? Okay.
Only roads.
Where? Here, this is a road.
That will also be a function of radius.
Yes. Let us see that. How? So first of all, let us assume this. We have assumption that this pressure gradient is a constant. This means dp by dr is a constant. Okay? Fine. So we can write dp upon dr equal to like delta p upon delta r. What this minus sign tells us is that you know that when you reach at the surface, so at r equal to r, p will be equal to pressure will be maximum, minimum, 0, A, B, both, none. Close to 0. E option. It will be 0. Of course. There is nothing outward of that, you have to push it down. There is no pressure. Okay? So at r equal to r, p equal to 0. And at r equal to 0, p equal to pc. So as r is increasing, p is decreasing. That's why we have one minus sign. And this minus sign will take care of this minus sign. This one. You can see here. Okay? So we have, you understood now? Simple now. It's like a P out minus PC upon R out minus R center. So P out is 0, PC is PC, R out is R central is 0. Minus sign got cancelled out. You got this? Simple. Second, we can assume that star has a constant density for our simplified calculation. In reality, it is not going to be the case, but let us assume for that. So if we assume that star has a constant density, so we can write rho at center given by simply total mass upon total volume. Total mass is m, total volume is this. Okay. What is happening? Okay. So if we put these rho values inside here and do the calculation, we end up with central pressure equal to this form. So you see, what is m? M is the total mass of the star. R is the radius of the star. So for the sun, we know these numbers. So this means if you supply these numbers here, we can calculate what will be the central pressure in the sun. Okay, so when we did it, it turns out to be around 3 into 10 to the power 14 Newton per meter square. Okay, this corresponds to about 10 to the power 9 times atmospheric pressure. So 1 kilogram on Earth will become 10 to the power 9 kilogram. Like it will not become, you will get a feeling of that. Here we are at 1 atmospheric pressure. There we will feel 10 to the power 9 atmospheric. Okay, you got it? See, we just calculated the central pressure of a star. And this is for the, we did this calculation for the star. You can use any other star. You can search in Google what is the mass of Betelgeuse, what is the radius of Betelgeuse, and then you can calculate what is the central pressure of Betelgeuse. You don't even have to go there. It's a very interesting thing. That's what we do in physics. Okay?
Sir, why are we approximating the pressure gradient to be constant?
For just for the easiness of calculation. If we want to, you mean density? No. Yeah, for the just for the calculations. We are assuming that as the radius is changing, the dr is changing, the way dp itself is the pressure change. This rate is not changing. It's an assumption. Sorry.
How can we be sure about that?
Yeah, as far as the star is in system, we can assume it. Locally, this may not be true, but globally, it will be. Okay. More if I will have it. Okay, third equation of energy generation. So you again let us consider this thin shell inside the star that having radius r and thickness dr. So let us assume Lr to be the rate of energy flow at radius r. Okay. And then at r plus dr radius, let us assume that the rate of energy flow is Lr plus dr. Okay. For the thin cell, our volume element will be 4 pi r square dr, understood? And dmr will be 4 pi r square rho r into dr. Simply multiplying this volume by the density. Alright? Now we are defining epsilon r as the energy released per unit mass per unit time. This is the local energy generation rate. Okay? So the rate of energy release will be, see, epsilon r is the energy released per unit mass per unit time. So energy released per unit time will be rate of energy release. This means we have to multiply epsilon r by mass. You understood? Epsilon r is the energy released per unit mass per unit time. We want energy released per unit time. So we have to multiply by mass. That's what is being done. We have epsilon r and we are multiplying by 4 pi r square rho r dr. Got it? And since energy is conserved, so Lr plus dr will be equal to Lr plus this local energy generation rate. That's what the third equation was. Fine. And again you do some rearrangements, you will end up with this equation. Fine. And you understand if r tends to if dr tends to 0, so this will be my dl by dr. Okay. This is the equation of energy generation.
In the atmosphere, some photons will be absorbed. So, in the energy.
No, see, usually these photons, so what the absorption that you are talking, that will be happening at the very, very outer layers. Here we are talking about inside the star. Understood? You got the idea? Okay. Whatever it is also up to some extent correct only. The radiation will not simply keep just moving through. There is another term called opacity. Okay. So the radiation will also interact with other photons. Okay. So I think I'm not covering, but I don't know whether anybody has told you that a photon which is produced at the center of the sun, okay, it takes about 10 to the power 8 years for this photon to reach at the surface. Okay, and then it takes 8 minutes to reach on. 10 to the power 8 years. It takes for the to be some because the medium is so dense, opacity is very high, that scattering takes place and the photon they are just randomly remaining inside the confined. So what you are telling is correct, but we are dealing with a very simple assumption. What you think? I'm coming to that. When we are solving these equations, this equation, structure equation, using realistic conditions, we cannot do it analytically. We have to go for numerical calculation because of these problems. Okay.
So
Fine.
for the the stellar spectrum also we ignore the atmosphere, right?
Sorry?
The stellar spectrum first we showed.
Yeah.
There also we ignore the atmosphere.
No, that is, it's like you are seeing a fireball which is emitting radiation at all wavelength, that is your continuum. And outside that star, this outer medium, because the photoscale is like it's not like inside the star. It is still a part of a star. Okay, but it is very old and it is not emitting radiation itself. So whatever radiation is passing through this cold medium, some of the part will be absorbed, depending on the chemical elements present in that outer medium. That's it. And that's why you will see the absorption lines. No, you didn't understand. No.
So what about the scattering?
Scattering will take place mainly inside the star, because the medium is dense. Outside the medium becomes very rare on scattering to take.
Because in the plot, in the stellar that spectrum, I didn't see any scattering.
No, the scattering I told you now, because this is, see, the scattering etc. is happening inside the stellar medium. It is not happening outside the star. So as an observer, we will not be seeing what is happening inside the star. We are, whatever spectrum that I showed you, it is what we observe. So this tells us there the continuum, what is the overall radiation coming from that star. How it was produced, how it was modified inside the star, that we have no information. So I will tell you one simple example of this. The effective temperature of the sun is around 5800 Kelvin. But does it mean that the radiation is produced at 5800 degree Kelvin? Inside the star, the temperature is around a million degree Kelvin. But if you observe the star, consider it's a black body, the radiation will peak at around 5800 angstrom, corresponds to 5000, not 5800 angstrom. It's like 5000 angstrom, which is a yellowish. That's why sun looks yellow, which corresponds around 5500, 5800 Kelvin. So this is the effective means. If you consider the sun to be a black body, you are standing outside, what will be the temperature of that? Emitting the radiation that we see. But it does not mean that the actual temperature of the sun is 5800. But this means whatever is happening inside the black body, we are not concerned. Got it? Whatever happens inside remains inside. Fine. Okay. So this is the expression I just told you about the energy generation rate. But we also have to keep in mind this epsilon. Okay. This also depends on, you can see this, I have not mentioned here. This epsilon, which is a local energy generation rate, it is also a function of density. You can see rho to the power alpha, and it is also a function of temperature. Now you start getting into how this is. It is not a simple different one equation. It is related with other ones, alpha and beta. And this alpha and beta depend on the specific nuclear reaction rate, whether it's a PP chain or CNO cycle. I don't know if you have studied PP chain. Everyone has studied PP chain. If you have not, I will teach you. Don't worry. Okay, basically these are again the way nuclear fusion happens. Okay. So depending on whether the nuclear fusion is happening via CNO cycle or nuclear fusion is happening via PP cycle, these alpha and beta will change. Okay, we will see tomorrow. Alright. Fourth equation. Fourth equation describes how energy is transported through the layers of the star. That is how the gas affects the radiation as it travels through. This is the question that was asked. Whether it is scattering, etc., whether it is local gas environment, how it is affecting the radiation. Okay, this is the fourth. Okay, so as usually teachers do in the class, they will do the derivation of like easy things, and the tough thing will say, okay, this is your paper. And in the exam, they will ask only that. Okay, so I am not going to type this now, and I'm sure that will show you the content rejected. Okay, so you have to do it. You just search Google what it is. So basically, you know what it is showing? It is showing the radial dependence of the temperature, which depends on something called kappa, then rho, then L. L is the energy flow, which is basically luminosity. Luminosity is nothing but energy per unit second. Okay, and then we have A, and then the speed of light, and temperature, then R is the radius. Here the parameter A is called the radiation constant, and it is given by 4 sigma by C, where sigma is the Stephen Boltzmann constant. So you know that people have already derived these things like long time. Okay, and kappa, this takes into account your opacity of the beam. That scattering, you see, scattering also has some sort of opacity. See, suppose photon is coming towards you, but it is not able to reach you. It just moved, it was diverted right or left somewhere. So you will not see that photon. So what you will think? You will think that photon was absorbed. Okay. So scattering also tells you about the opacity of the medium. Okay. So here kappa is the absorption coefficient. It depends on the sigma t. Sigma t is the Thomson cross section. You know Thomson cross section? No. Okay. I don't worry. Radiative process force. I think that faculty will teach. It is a cross section found by Thomson, J.C. Thomson. So it's a Thomson cross section. Basically, it's very simple formula 8 pi by 3 r square. Where r is the like electron radius and it's like 0 like some arbitrary. And mp is the mass of photon. So you see, this equation tells us about how the temperature changes as a function of radius and how it depends on the opacity of the medium. Okay, so you can get a feeling here that this fourth equation tells how the radiation is transported as it passes through the layers of the star. Okay, fine. Okay. So we have 4 equations and we have 4 unknowns. What are 4 unknowns? MR. You know, first equation was DMR by DR. Second one was something, and then ER, and the fourth was DT by DR. Okay. So we have 4 equations and 4 unknowns. Provided we know P, kappa, and epsilon. P is the pressure. Provided, but this is never provided. Okay. So you know that when you want to solve a differential equation with boundary conditions. What are the boundary conditions we have? Again, we have the boundary conditions. As center of the star, M tends to 0, L tends to 0. There is no mass inside that center. You are already at center. What else will be inside? Okay? And luminosity will also be almost 0 because there is nothing to it. You are already you are at the bottom. Everything is on top of you. At the surface of the star, temperature is reaching around T surface. Pressure will tend to 0. Because nothing outside to push the surface down, and the density also will change to 0 because all the medium is below. Okay, these are boundary conditions. However, the calculation of full scalar, so you understand by using these 4 equations and knowing some of these boundary conditions, and provided you know pressure variation and the opacity and energy generation rate, you can define the overall structure of the star. The structure of the star means how the mass is changing as a function of radius, how the temperature is changing, how etc. number of how density is changing, etc. These things. Okay, so like solving these equations are we in a good language we call it's called solving stellar models. Okay, because we have never gone to any star, we have never been to any like we are standing on the star and we are watching what is happening. So we have developed models, and if my model is correct, then my model should predict something observationally, and it should be found by observation. That's what we do in theory and observation. Theoretical people propose something, they predict, like Einstein predicted in 1950 gravitational waves. It took us 100 years. But in 2050, it was observationally correct that gravitational waves do exist. Okay? That's what we do. So stellar models, like some theoretical experts, they develop some set of stellar models. And then observationally, we are seeing whether we can. Fine? Alright.
The PS, so is the surface temperature, is that the one we get from the black body spectrum? How do you know that?
From the model. See, this PS is the surface temperature. I don't know whether like the surface temperature of the sun is 58 degree Kelvin. I guess probably. It is probably that. Yes. Probably. Good question. Very good question. Probably it is the like no. Yes, is the surface temperature that I know. But when if you are asking whether this is the black body temperature, effective temperature of the star, that I am not really sure because effective temperature means that effective temperature of a something is the temperature of the black body which is emitting the same amount of radiation emitted by that body. That's how this effective temperature is defined. Okay, but I will have to check. It's a one-line question. You can search it Google. What is the surface temperature of the sun? See what number comes out. If it comes out with 58 I don't think it will be 508 degrees. Okay, fine. Time scales. Last thing. Whatever. So see, in the life of a star, there are three important time scales. Okay, first is called the dynamical time scale. What is dynamical time scale? The time scale on which a star would expand or contract if it were not in equilibrium. Say for example, what is the meaning of that? Suppose there is a star in equilibrium, fine. There is something like inside energy is being produced via nuclear fusion. So there is outward radiation pressure, gas pressure, which is holding against the inward gravitational force. Fine. Suppose somehow this central engine which is producing it, suppose somehow it is switched off. Then what is the meaning of this? There is nothing to stop the gravity now. So suddenly the entire star will free fall. It will be like it will collapse. So this time scale tells us how much time it will take the star to collapse. You got it? Or in other way, suppose if you want to think, suppose because of some unknown mechanism, suddenly this gravitational force becomes zero. Then there is nothing to stop the outward force. Suddenly the entire star will explode. So how much time it will take the entire star to lose its equilibrium? It will lose its shape. This tells us about this dynamical time. So you understand? We have a characteristic radius of the star, and then since if there is nothing to stop gravity, we will have a free fall. It's like escape velocity, isn't it? Okay. So we are. This means this T dynamical, or say here shown the tau, is R, the radius of the star, divided by the escape velocity. Fine. Now the escape velocity from the surface of the star is square root of 2 gm by r. This we all know. All right. So you can supply this number. It will give you T dynamical equal to square root of r cube upon 2 gm. Okay. So in fact you can calculate this for the sun because we know m, we know r. If you do it for the sun, it turns out 1100 seconds. That's it. It will take only 1100 seconds for the entire sun to collapse. Got my point? Okay. You will appreciate this number just very soon. Second is the thermal time scale. Okay. All right. What is this time scale? This time scale tells us about a similar thing. Suppose in a star, energy is produced via some nuclear fusion. Okay, so the entire star is emitting radiation. At some point, some big person came and the fellow switched off the switched off. Okay, but you understand from intuition that this star will keep emitting the radiation for some time. Even there is no new source of energy, but whatever energy it has, it will take some time for the star to emit. This time scale is called thermal time scale. Okay. The total gravitational energy available is gm square by r. You know that gm1 m2 upon r. Okay. So if the energy release rate or say luminosity is L, I told you luminosity is energy released per unit time. So this is the energy release rate. You have a total energy gm square by r. This is the gravitational potential energy of the system. Now you have to release this entire energy via radiation and your luminosity L. So how much time it will take? Will be total energy divided by energy release rate. Okay, you are fine. You fine? Okay. So gm square by r and L. Got it? Now for the sun, we know sun's luminosity, we know sun's radius, we know sun's mass. So we can calculate what is the thermal time scale for sun. For the sun, it turns out to be around 3 into 10 to the power 7 years, which is much less than the age of Earth. This means at least for now we know that in the sun's interior that engine has not switched off. Okay? Otherwise, how will we survive right now? We will not be surviving. Okay? So at least you should be happy. Okay, this is still going on. Whatever is happening is happening. Now, third is the nuclear time scale. This time needed to exhaust nuclear fuel at the current rate. The sun has some hydrogen. It is converting the hydrogen to helium. You know that you understand after some time, may not be right now, some billion years from now. Slowly, but all the hydrogen will be converted to helium. Okay? So this means there is no more fuel left. So this time scale tells us how much time it will take for the star to consume its entire fuel, given its consumption rate, what we know today. Okay, suppose in a vehicle you have a petrol tank completely full. Now you are driving. So how long you can? This is the meaning of that. Right? Now you understand there will be an efficiency factor eta, because not your 100% of your mass will be converted to energy. It's like only you can see it's not even 1%. So I think I will only teach you that nuclear fusion is not the most efficient way of producing energy. Even nuclear fusion is not. See how you can get energy? Burning the coal, burning wood, nuclear fusion. But you know that there are other processes happening in the universe which are much more efficient than the nuclear fusion. Okay? We will study later. Alright. So when we do this calculation, it turns out to be for the sun, it is around 10 to the power 10 billion years. Sorry, 10 to the power 10 years. Which is 10 billion years. Which is the which we call as this is the age of the sun, total age of the sun. Right now we say the age of the sun is around 5 billion years. Okay, you got it. So one thing what we have learned so far is that dynamical time scale is much smaller than the thermal time scale, and thermal time scale is much smaller than the nuclear time scale. What is the meaning of this? Dynamical time scale tells us about the time scale for the collapsing star. Supernova. I will teach you supernova. How exactly it happens. Okay, so you understand? In supernova, actually before star goes outward, the entire star implodes inwards. So the time scale is 1100 seconds for the entire sun collapse. Thermal time scale, this tells about the time scale of a star before nuclear fusion started. That means the star before the star entered into the main sequence. Main sequence, you remember? So in the main sequence, the condition is that your hydrogen burning should start. Then only the star has entered the main sequence. So this time scale tells us about the life of the star before it reaches the main sequence. Okay? And finally, nuclear time scale tells us about the duration. As long as your nuclear fusion keeps happening. So this means as long as your hydrogen is getting burned into helium, the star will remain in the main sequence. So this tells us about the time during which stars remain in this sequence. Once all the hydrogen is consumed, then you will start moving away from the sequence. Got it? We will study those things in detail. Okay. So most of the time, they are in hydrostatic equilibrium and thermal equilibrium. Their changes happen very slowly, and their composition also does not change very drastically on a short time scale. It will, admittedly, it will change, but on a very long period of time, 10 to 10 years. Okay? If something happens to a star faster than one of these time scales, could be because of any reason, we do not know, then the equilibrium is disturbed. Okay? And when equilibrium is disturbed, then violent things happen. This is a rule of nature. Okay? How it can happen? Suppose there is a supernova happened nearby. I mean like a cosmically nearby, not in the next room. Okay? Suppose some supernova happens, the supernova explosion will release lot of energy and the shock waves will develop. And the poor fellow, some star is in some corner where the poor fellow is living its life, and suddenly some shock is in the entire media. And this fellow got and hits on the star. So understand that the entire equilibrium is disturbed. So the life of the star will be affected. So its evolution will not remain same as it was supposed to be. Okay? Or say binary interaction. Suppose there are two stars nearby, but the other guy is bigger one. So since it is bigger one, it will have a more higher, like a larger force of gravity. It will start attracting the mass from the smaller star. Okay? So this is how binary stars evolve and all. So this is another field of physics. You got the idea, no? So this means as far as these time scales are followed, like we are talking about the laws of the nature. As far as stars are like they are respecting these time scales, nothing nonsense is happening around. All the four equations are being like followed properly, system is in equilibrium, the life is peacefully going along the main sequence and all. Something else happens, then the system is disturbed and the life of star will be affected. How it will affect, we'll study in that class. Okay? That's all for that. Thank you. Questions. First, I will take up the question from the online participant. If you have any questions, please let me know.
Sure. I'll ask them to raise their hand or type in the questions. So refresher course participants, you can either raise your hand and I'll unmute you, or you can type in your questions in the chat.
Okay, offline people. Questions? No questions? Yeah, go ahead. Go ahead.
So in the four equations that are happening, are all of them valid for the entire term?
See, like, we are calculating the different crystal quantities as a function of radius. Okay. So you can determine the structure as a function of radius.
So with in the energy equation, there is like the opacity factor that's the energy transport.
Yeah. So see, energy generation, what it has to do with capacity. You think, suppose some element is producing energy. Production does not require opacity or scattering will happen when the energy is produced. And now this energy wants to be transported. Then only your opacity, scattering, etc. See, that is the and you see, these four equations are not completely independent. When you are solving one, you may have to put some number from the first. So, putting equation 1 into equation 4, then inserting this into equation 3, like the way they talk to each other.
Also with the energy of this sequence, there is a conservation of energy. So if opacity is present in the energy, like now
No. So you imagine a situation. That's what you imagine. You imagine this is suppose some element. Okay. I am not bothered how energy is coming through like below lower layers. I am only concerned just below this layer. What is the energy that I am receiving? How I am doing, I am not bothered. Whatever I am receiving and whatever I am thinking above this layer.
the layer is very thin, so that no absorption.
Absorption or emission can happen. That's why we have a local energy generation rate. It could be positive. If it is positive, this means that layer is emitting. If it is negative, it is absorbed. Both of them are. When you talk about opacity or scattering, this means when you are looking at the overall structure. Okay, from R equal to R1, R equal to R2, how temperature is varying, and you understand this temperature variation will depend on the opacity. Okay, suppose at this level some radiation is happening, and you want to measure here, but in between there is a very dense medium. So here the temperature will be relatively lower because most of photons are not able to reach here. Understood? Now we are seeing how temperature is varying. Okay, you got the idea? Next.
Sir, you said that thermodynamics talks about the three main sequence lifetime. What doesn't the
What
star
does it mean?
start on the main sequence?
No.
So where is it before?
Where it is before that we study tomorrow only. See, a star in the beginning, a star does not come out of nowhere. Okay, so the question is how stars are formed. So I will teach you in detail. I will teach you tomorrow this. But very quickly I will tell you. See, there are in the interstellar medium. Okay, there are clouds of gas and dust, which because of some mechanism, due to some process, they start collapsing. So in the beginning, you have a very small physical thing where nuclear fusion is not taking place. Okay, so this means system is not in equilibrium, but it is a small something. And then suppose there is a medium around it, and you have something which is gravitationally like more heavy, it will pull matter. So slowly it will grow. When it will grow, its mass will grow. More mass means more gravity. You understand? So in a very layman language, your temperature will start increasing inside. Okay, this means this is the time when you are in a pre-main sequence stage. You have a still main sequence will start only when you will start burning hydrogen to helium. So and for hydrogen to helium nuclear fusion, a certain minimum temperature is needed. I am going to teach you tomorrow that you see those two hydrogen atoms, they will not simply fuse each other. They will not simply fuse. Why? Because of the Coulomb barrier. Okay? You can plot the Coulomb potential energy now. I will show you tomorrow. Got it? So this means you have to push them close to each other until they reach a distance of I think 10 to the power minus 15 meter. And, okay? And once they reach there, then you cannot pull them apart. Certainly. Got it? Okay? So until you have this fusion happening, and when fusion will not happen until you have the temperature needed for the hydrogen atom to fuse. Till then there is no fusion. So till then there is nothing to stop gravity. So the system will keep collapsing to smaller and smaller, but its gravitational influence is increasing, so it will keep attracting more and more matter, down to that small thing, which is also called protostar. Okay, I will teach you in detail. I will teach you. Okay, questions?
In the beginning, you showed the spectrum of a star, and you said there were the Balmer lines, which is the second energy level, hydrogen, right?
Okay.
So why do they not go to the ground state?
No, they go. What do they do? You get H alpha. See, we get H alpha, H beta, H gamma, H delta. We get all emissions.
Okay, not just one.
Not only H beta, we get all of it. Okay. In fact, we also get Lyman alpha. This means your atom has gone out of the system. Okay, we get all emissions.
That as mass size increases, the temperature decreases because of the more surface area.
Okay.
So, but in main sequence, it's different cases. When size increases, it hotter. And after that,
Let us be na.
So as size increases, the temperature increases.
See, change in temperature here and see dependence of temperature with size. Here the basic assumption is that the luminosity remains more or less constant. You see this horizontal giant branch? You see, this means y-axis value is more or less same. Luminosity means what? Total energy. when you have a smaller area, so you can emit only smaller radiation. So most of the radiation will remain inside you. Your temperature will be high. Now, you are producing the same energy, but your surface area is much higher. Which means what? This time you can emit more radiation. You can emit more radiation. So your temperature will come down. But the assumption here is that the luminosity of the, like your energy production rate is same. It is not. When what you see along the main sequence, that energy generation rate, the luminosity itself is changing. What I said, cooler surface for the larger star, but that does not mean that larger, in general, large stars have cool surface. No. Assuming that if the luminosity of the star remains constant, then bigger star will have lesser. And if luminosity does not remain constant, then it will not be the case. Okay? So got it?
Sir, in the absorption line spectrum of hydrogen that you saw, you said that it will go much deeper. Has it got anything to do with the chemical composition, or is it just about the types or something? The relative spins are different for different types of stars, as you said. Has it got anything to do with the chemical composition, or it's just about the
not only
temperature?
chemical composition, it also depends on the density of the medium. Didn't it? Density of medium also matters. See, chemical composition will, suppose radiation is coming and you have in the medium, suppose this is just say for example only magnesium. So magnesium will absorb photon at certain frequency, characteristic frequency, and you will see a certain dip. But the width of the dip, or say the depth of that dip, okay, depends on the thickness of the medium. Okay, the other parameters will come. So this strength of the absorption line depends on the local medium. Okay, so this means by taking the optical spectrum and studying the spectra of stars, we can study the property of that medium, from where this radiation is coming, through which the radiation is coming. Okay. Last question. Yeah.
In the spectra, when will it have absorption and when will it have emission?
Yes, you know the physics of emission spectrum and absorption spectrum, correct? Yes, no. No problem. If you don't know anything, yeah. But anyway, I'm going to teach you also. But when next week. Okay. So you know the question is that when we see emission spectrum, when we see absorption spectrum. You know? Okay. Fine. See, for absorption spectrum, the concept is very simple. You have a continuous radiation coming, which is like say interior of the star, and then you have a cooler atmosphere outside. Okay, and when the radiation passes through, so the molecules or atoms inside that medium, they will absorb some of the radiation. Okay, and they will go to high state. They will also emit. I'm not concerned about that. But what I'm seeing, I'm standing next to you. So the total radiation minus some absorption is what we are going to see. This is the absorption spectrum. Okay, let me try. Do I have I have that. Okay, so say for example, you have this is the incandescent sun, emitting at all frequencies, continuous radiation. You have some medium. Okay, you are standing here with a telescope. What you will see? Like this, absorption lines. You are standing here. You have a telescope like this. Here you will see. Because this is the same gas, it will also emit some radiation. But in this case, I am not bothered about this. See, this means you can have the same medium is also emitting and absorbing also. Yes, but the question is that what is dominating? What is dominating? Okay, so this depends on the density of the medium, property of the medium. We will study emission line spectrum when we study active galaxies. So see, you know that usually galaxies consist of stars. Okay, so that's why if you take a spectrum of a galaxy, okay, hold on. Prakash, is there Any question from the online participant?
No.
No?
None.
Okay. So then I will log out from my Google.